Hi, here's another power supply review, and this time around on the bench is a Topshak 3010EC 30 volts 10 amps programmable power supply. This unit was provided to me by Banggood, and what attracted my attention was the specs and the price point. Considering this unit is currently on sale for just under $70, it is certainly a lot of bang for the buck, especially considering that it is programmable. So we will put it through its pace and see how well it does. Later on, we will open it up and take a look inside. Now, spoiler alert, when I glanced at the product page, it appears that the main PCB used in this power supply is quite similar, if not identical, to the Kaiweit's power supply that I did a review on a few months back. So this means we can reasonably assume it will perform just as well and should not have any major issues. By the way, the model number of this unit is LW-3010EC. It also suggests that all these power supplies can all trace back to the same origin, which in this case I believe is the Longwei power supply. And this kind of rebranding is very common in these Chinese electronics. I believe the Topshak brand is tied to Banggood, kind of like the Amazon Basics branding. This unit came with a manual, a thumb drive that has the PC software along with a USB communication cable. And yes, this programmable power supply does support programming its output via PC, which is certainly not too shabby. We will probably take a quick look later. The first thing I wanted to comment on is the form factor of this power supply. And if you take a look side by side, it is remarkably small compared to the Kaiweit ones I did a review on last time. And if you look at the dimensions here, the Kaiweit ones is not just wider, it is actually significantly deeper. Now the back side is almost flush, and you can see that it has about 1 inch more depth compared to the Topshak power supply here. And keep in mind that both of these power supplies have very similar specs in terms of the outputs. The size difference is largely due to the fact that in the Kaiweit's power supply, the main board is mounted at the bottom instead of vertically, and thus wasted a lot of space. Another complaint I had about the Kaiweit's is that because of the use of these sets of potentiometers to do the coarse and fine settings of the voltage and current output, it takes quite a bit of patience to set to your desired settings accurately. Because this Topshak one is purely digital, this should not be an issue with this power supply. Another thing you will notice immediately is instead of using these binding posts for the output terminals, you get these shrouded banana sockets. Personally, I prefer the more traditional binding posts just because they are more versatile. But these sockets will get the job done as well. Just remember that you will have to use appropriate wires with banana plugs instead of some ad hoc loose wires with spade connectors. This does limit your choice a little, but not much. By the way, although you only get the positive and negative sockets on the front, you do get a chassis-connected earth terminal at the back here, as you can see. Unfortunately, given the socket design, it is not going to be as convenient as a standard binding post configuration if you need to connect either of the output to the ground, as you can't just easily hook them up together without adding additional wiring here. For most of electronics work though, it probably doesn't matter much leaving the output floating, but for safety reasons, it might be a good idea to connect either the positive or negative terminal to the earth ground so that in the event the mains isolation becomes compromised, the fuse would blow. Alright, without further ado, let's power it up and take a closer look. Okay, before powering it up, let's take a look at the setup here. In the middle, this is the power supply, and the output, you can see that I have two sets of banana leads stacked up. One set right close to the output. This set goes to the multimeter here to measure the output voltage at the terminal. And the other set of leads goes to the electronic loads. So later on, we can put some loads on and see how the power supply behaves. Now let me power it on. And I think the 30 volts 10 amps are the factory default output. So let's turn it on. And by the way, the setting is quite intuitive. Let's turn the output on. I would expect it to see the 30 volts on the multimeter, no problem. And so right now, let's just take a peek at how this works. So if I twist this knob, you can see that the output is live. I hate this sound. Let me see if I can turn it off. Let me refer to the menu. One moment, please. Yeah, as it turned out, you can turn off the sound. So that is done by pressing this OCP button till it beeps. And right now the output sound should be off. So let's see that. So again, we can, yep, so now indeed there's no more annoying sound. So you can see that you can adjust this knob and the output changes automatically. How this works is actually the setting is automatically set, the memory that is, when the digit stops flashing. So right now in theory, if I turn it off, let's power it off, and we power it back on, the first memory going to be showing the 2976 as we had before. Yep, so that's what it was. So this is actually very, very easy to do, but you just need to remember that when you set this output and everything you change is automatically remembered by one of these memory slots that you currently are on. So let's set the output voltage to be 10 volts. And you can either do this by the last digit, of course it's going to take quite a bit, or you can press this rotary encoder to do it at the desired location, so you can set it faster. So this is actually not all that bad, and it does take some use too, but you know, I would have preferred they have some kind of button like this electronic load. You can kind of switch the digit here, but it does get the job done. So let's set it to 10 volts, let's say, and let's enable the output again. And you probably heard that relay click. So the output is actually controlled physically by a relay switch. So if I turn the output off, you will hear the relay clicks back. Yep. So this is to ensure that the output is disconnected and connected. Now let's enable the output. And by default, the overcurrent protection is actually off. So in order to enable it, let's press this button. So it turns blue. Now, supposedly the overcurrent is at 5 amps that we set before. So now let me ramp up the electronic load, and we will see if the setting is accurate. So let's start it ramping up the current. Now we're at 1 amp. And you will notice a little bit of voltage drop on the wiring here, even though we're measuring at the terminal, but obviously the banana plug has some length here. So we're not, technically speaking, measuring at the output itself, which is to be expected. So let's start it ramping up a little bit more. Right now it's at 1 amp, and you can see everything largely agrees. Let's do 2 amps. No problem. And let's go directly to 5, which is the overcurrent limit we set at. So now we're at 4.91, so if I change it to 5, I would expect the output to collapse. Which is indeed is working as expected. Of course, now it is very annoying, and the output turned off, and I'm not sure how to disable the sound. Okay, I have to press the OCP again to disable the alarm. So it appears the overcurrent protection is working as expected. Now let me set that current to be the maximum so that we can see how well it behaves under the maximum load. So let's change the current setting to 10 amp, which is the maximum. And I think you can actually get a little bit above it. Let me just see here. Yeah, you can. So let's see how much we can get above the 10 amps. Okay, so the maximum is 5. And so now we're at the 10.5 amps. So let's again turn on the electronic load and see what the situation is like. So now we're at 2.3 amps as we said before. Now we keep increasing the output amperage. So we're at, let's just go directly to 10, as that's the maximum that is specified. And you can see that at the maximum current we do have about 0.2 volt voltage drop. And of course right now the fan just kicked off in this power supply. And let me see if it's power supply or it is electronic load. Yeah, right now that's the fan from the power supply. And you will see we do have this 0.2 volt voltage drop at the terminal right here. That drop is not from the wire. As I mentioned earlier, we're actually plugged directly in here. So this is what the meter is reading out from. The voltage drop from the wiring is actually quite significant. You can read from the electronic load. Right now, at the end of the wire, we're only reading about 9 volts. So that is about a 1 volt drop across the length of the wire. And now the fan from the electronic load also kicked off. So let me increase the output voltage right now and just increase it to about 30 volts. We may not hit that actual 30 volt mark because the maximum dissipation from the electronic load is just at 300 watts. But let's try that to see what we get here. Now, the one thing that you notice is this setting for the output is actually live. So you just need to be very careful when you are connected to your circuit to make sure that you don't accidentally switch the setting to affect your circuit operation. So let's turn it up all the way to, let's do it 29 volts first, as I want this number to be under 300 watts. Let's see, 300 watts. Okay, that's just about right. So that's at our maximum spec'd power supply output. As you can see, everything is holding up pretty well. Now let's take a look at the power on characteristics of this power supply. And as you can see, the overall power on curve is relatively smooth, but we do have these sharp noises here, and I wanted to take a closer look at what is going on. Now I'm just doing a quick measurement at the output repo, and you can see it's actually quite significant. I had the readings on, and you can see it is at about 100 millivolts RMS. Now, according to the manual here, it is supposed to be less than 50 volts RMS, and it depends on your current, of course, but nevertheless this is a little bit higher. Of course, as I mentioned earlier, that typically you measure the repo using a 50 ohm termination, which we don't have, but let's add a little bit load to see if that has any effect on the reading here. So for that, I'm going to hook up a 100 ohm load, and yeah, it doesn't really have any significant impact on the RMS. It dropped a little bit by about 20%, but nevertheless, this power supply looks to be quite noisy. And the next experiment I want to do is to see how well it does the overcurrent protection. For that, I hooked up a 100 ohm resistor to the output, and right now the output voltage is set at 30 volts. The maximum current I'm setting at is 0.1 amp. So I would expect as soon as I turn it on, it would trigger the overcurrent protection. And the question is how fast it can turn off the output when it detects there's an overcurrent situation, and therefore protect the output device. So let's turn on the overcurrent protection and power it down, and let's take a look. So as you can see, we immediately triggered the overcurrent protection, and the oscilloscope did not get triggered. So that's actually a good sign. So let me try it again to see if we have any consistent result here. No, this time you can see that there is a significant delay over the output enabled and also the relay click to shut the output down. So let's take a look at what we have measured on the oscilloscope here. So we can see that, let me just zoom it in a little bit. So according to this waveform, yeah, it did not capture the entire thing, but you can nevertheless see that we have roughly about over 1 division. So it actually took a little bit over half a second to shut the output down. And the output actually, by the look of it, increased all the way to about 2 volts. The output I'm measuring is across the resistor. This resistor is at 100 ohm, so therefore you can get an idea of the significant voltage across the resistor. So actually at this time it's 200 milliamp instead of the 100 milliamps that we specified here. That experiment is just to demonstrate that you shouldn't always trust your current protection on your power supply to protect any sensitive devices hooked up at the output. As in this case, the current did exceed the specified current by 100% for about half a second. Well, folks, a little bit of change of plan here. I was going to give this applied PC software a test with this power supply, but when I plugged in the thumb drive to a Windows computer, and yes, the software is again Windows only, it reported it contained a virus. So obviously, we're not going to install the software. Now, I would hope the virus is just accidental, not something deliberately put in. And if I do find a clean version of the install somewhere, I will definitely report back. Now let's move on to the teardown. So now you can see it inside of this power supply. And just by the glance of this main board, it looks pretty much identical to the main board in that Kaiwit power supply that we did teardown a while ago. And I'm going to put a picture on the screen here, and you can see that side by side. And just by my memory, I remembered seeing all these components on that board as well. So let's take a look at the back of this board. Yep. And we also have these three resistors on the board, which is exactly the same as what we had on that Kaiwit power supply board. So let's see if we can find any markings. And if you take a look at the silk screen here, it says a long-way switching power mode supply. So clearly this board is also sourced from long-way, just as they did in that Kaiwit's power supply. So what I think I'm going to do next is just remove a few more screws so that we can take the boards out and take a look a little bit more clearly. Now that I have loosened the front panel and also removed the sideboard out of the way, now you can see the main board a little bit more clearly. And indeed, this long-way board is almost identical to the one we found in the Kaiwit's power supply. And the only difference is that the 5 volts USB output is actually implemented on this separate board instead of everything on the main board. And the good news is that it appears this kind of a power supply design is quite mature. In fact, they have put the same circuit board in multiple power supplies. The main power supply actually is following a very traditional design. You have the switching elements here, and you have your main pulse transformer. And on the secondary side, we have this chip, which is a SG3525 PWM controller that is regulating the output. On this main board, we essentially have two power supplies. One is the upper 2/3 that we just mentioned about. That's your main switching power supply. And the other, if you follow this common mode choke at the bottom here, you will see this TNY2ADGN. That's another offline switcher, which provides power to the auxiliary circuitry. And also, as we mentioned earlier, the charger output for the USB is powered independently by this board, which utilizes a DK112 switching power supply controller. And here's your digital controller board that controls the front panel and also the power supply voltage and current settings. And by the look of it, it is powered by this single STC15F2K60S2 microcontroller. This microcontroller has built-in ADC, which can be used to measure the output from the main power supply module. It also has built-in PWM. I assume that is used as a DAC, as I don't see any discrete DAC on this main board here, so that DAC would be used to set the output voltage and current. Earlier, I showed you that this power supply supports PC communication that is accomplished by the USB port included at the back of the unit. And that USB is connected through this ribbon cable right to the front panel here. And if you're curious what that chip is doing there, whether or not it's isolating the USB, you will be disappointed. That's not a USB isolator. So in fact, the USB is not isolated from the circuit here. And that is just merely a LM356 op-amp. And by the look of it, we have a dual supply rail on this digital board here. These two are 78.5 and 79.85, two linear regulators generating the plus and minus 5 volts. And that plus minus voltage is probably used for the op-amp only. as all these chips are just 595 shift registers. And that pretty much concludes this teardown. I will put some high-resolution pictures on my website for those who wanted to take a closer look. For those who are interested in getting one of these Topshak power supplies, you can check out the link in the description below. In my opinion, this power supply is definitely better than the Kaiwi's one I reviewed earlier, given its digital control interface, which allows more precise voltage and current output settings. I hope you enjoyed the video. Please remember to give it a big thumbs up, subscribe, and share. That would greatly help out the channel and enable me to put out more content like this in the future. I will catch up with you next time.